Recording.
All right.
Good observation there.
All right. Because there is a connection to this unit and last unit, and it still deals with force. But here, the whole chapter is about work and energy, and a lot of good demonstrations to show you. And again, like last time, there's 4 labs, so you get your hands on some stuff here. So let's just start out real quickly. Impulse, we know that. That deals with applying a force over a period of time. So how hard you push it, and for how long a period of time do you do that? Work does deal with force as well, but not force in time, force in, any guesses?
Energy.
Well, yeah, work and energy are definitely related. Instead of looking at how long a time period you exerted force, you could also look at how long a distance you exerted force, how far, and that's what it is. So that's work doesn't deal with force in time. Work deals with force in distance, as in how far did you push the object, not for how long a period of time did you do it. Okay. So back in Monum, we looked at how long a time period. Now we're going to look at actually how far you push something. And it should be kind of obvious that the further you push something, the more work you do on it. Just as an example, I want to lift something up. This isn't very heavy, but oh, that took a little bit of work. Hey, that took more work because I moved it further. That's all it is. In fact, if the two things that matter are force and distance, then I wonder what we might do to them to make a formula for work. Yeah, what did you do with force and time for impulse? You multiply them together. That's what we do for force and distance. We multiply them together. So the formula for work is force times distance. I'm going to leave a little bit of room in here because there's some other things we'd like to write down. But yeah, force times distance so far is the formula for work. Which kind of makes sense. It takes more force to move bigger things, heavier things, more massive things. So more massive things take more work to move them. And obviously moving something a little bit or moving it all the way down the hall are two different things. And so the distance matters as well. We had units for impulse and momentum. We didn't like them, but they were kilograms times meters per second. Yeah. Well, there's obviously going to be units for work as well. We could do it this way. Force is measured in newtons, and distance is measured in meters. So we could just call it newtons times meters. That is a completely legitimate unit for work. You can measure newton times meters. Some people would just call it newton dash meters. That does not say subtraction. It's like a hyphenated last name. You just say newton meters, all one word. But they wanted to honor somebody. So instead of calling it newton meters, they measured it in, anybody know? Yeah, it's measured in joules. Yep. Looks like joules. We say joules, and it should be the same joules that you recognize from chemistry. I don't know if you use calories or not in chemistry, but I know you use joules. I've seen that on the back and forth. Joules are used for it. Okay?
So it's J equals F times D?
Careful. It's W equals F times D. But the units are capital J. Yeah, you can just write capital J if you want to do that. But you wouldn't write J equals, you'd write W equals. Okay, good question. There's a couple other things to keep in mind. And that's why we're going to add to this formula here. Okay? Ready? Positive work. Which way was I pushing on the object? Up. And which way did it move? Up. Now which way am I pushing? I am? I'm still pushing up. I'd have to push like this to push down. I'm still pushing up, but the object's moving down. That's negative work. The object's getting less energy than it had before. Okay? Positive work, negative work. All right, you ready? Any guesses? 0. Yeah, but I need yeah, right. Because which way am I pushing? Up. Yeah, I'm pushing up. Pushing up. Which way is the object moving? Oh, which way is the object moving? Oh, sideways. So the push is up and the movement's sideways, and those happen to be perpendicular to each other. So the first time, positive work, the push was that way and the movement was that way, that's positive work. The second time through, the push was this way, but the movement was that way. Those are opposites of each other, that's why it's negative work. And the third time through, I'm pushing up, but the object's moving sideways, and those two are perpendicular to each other, that's considered zero work. The other thing to consider, just like we did for impulse, it's the average force that matters. I would really doubt that when I push this up, I can push with exactly the same force the whole time. That's probably not going to happen. It might be close, but I would bet you, even if I did this, I would bet you if I drew a graph of the force that I exerted, it probably goes kind of like this. It doesn't stay exactly the same the whole time, and I don't want to take care of all the little forces. So all we're going to do is go, well, the average, we'll just take that right there and call it good enough. It's close enough. If you take the average force, no problem. The other thing that matters is some directional stuff. This goes back to vectors. Okay, so as an example, we have a wagon like this, and you pull on the handle, which we tend to do. Okay? Not many people that I know get down and pull on the wagon completely sideways. We tend to pull on stuff like wagons like this. Well, the pull is this way, but the wagon tends to move which way? Just sideways. So the key is when you pull up and to the right, you are pulling up and to the right. And we call those the two components. Yeah, we call those two components. We've used those word before. Components. So the question is this. This is the overall force, but this is the force in the x direction, and this is the force in the y direction. If you're going to use our formula for work, which says take the force times the distance, and the wagon moves, let's say, from here over to there, which force are you going to use? The overall force, the force in the x direction, and the force in the y direction? Any ideas? If the wagon's going to move this way, which piece of that would you like to use?
Half of X.
Yeah. So that's the only part that you care about. It turns out that this piece doesn't do any work whatsoever. Why? Well, like I just showed you before, the wagon's moving sideways, but that force is up and down, and those are 90 degrees to each other. Just like this, when they pushed up and moved sideways, didn't do any work whatsoever. So this piece does some work, this component does some work, but that part doesn't do any work at all. So we generally, the way we've written this before, not only is this a subscript average force, but another subscript looks like this. That's the symbol for parallel lines from your math class. So we say it, the average force parallel to the direction of motion. It's two subscripts if you can handle that. That's what matters. So only the part of the force that actually is in the same direction as the object moving counts. Anything that's not in that direction, that doesn't count. So the book might have a slightly easier definition. You probably just have force times distance, but these are the two things that also make a difference as we go along. So, you ready? Let's push for the 100 newtons of force for 5 minutes, but the object didn't move. How much work did I do? 0. It's got to move. Right? It says, look, you have to move the thing to do some work. So you can push against the wall all day if you want to, and you won't do any work on that object. You might do some work on the muscle fibers inside your body, but you're not doing any work on that object. So you have to exert force, and it's got to move. You could look at it this way. Could you say that the Earth just did work on the marker?
Yes.
And did it exert a force on the marker?
Yeah.
Yeah. Did it move it?
Yeah.
Yeah. You could look at it that way. You could say the Earth did work in pulling the marker down, and the marker did work in.
Over here.
There? Okay. Just a second. All right. We will get that formula in there in a little bit. Let's skip power for now. We can come back and do that tomorrow. And let's remind you of some stuff that you already know from before and tie it to something that's new for today. We've looked at the area under the speed versus time graph. Let's see. Slope of the speed graph is the acceleration, but turn around. The area under the speed graph is the
Change of displacement.
yeah, it's change in displacement, which is distance A, right? So we do a speed versus time graph, and we've done this before. As an example for something that maybe does this and then stays like this. If you want to figure out how far that person went, that's all you have to do is, I'm not saying it's easy, but find all that area underneath that graph, and that will tell you the distance traveled. And it's kind of weird, because you know what? Distance equals, how are those two related? Distance equals average speed times time. And then we came over and looked at force versus time graphs in the last chapter. And maybe a force graph looks like this. Maybe you start with a really big force and come down to 0. And if you take average force times time, what do you find? You remember from the last chapter? Okay, if you take average force times time, what do you find from last chapter? Change in momentum. So, but taking average force times time and finding the area under this graph turns out to be exactly the same thing. Because here's one way to look at this. I could take the area underneath that graph, and that's a triangle. We could take 1/2 times base times height. Isn't the average force probably something right about there, though? Isn't that probably the average force? Right? Well, watch what happens if I draw a graph that goes all the way across. If I took average force times time, wouldn't I find the area of that rectangle right there? Did you know that the area of this rectangle and the area of this triangle are exactly the same? Can you see how this triangle would actually fit in there? If you take the average force times the time, right? Average force is the height times the time. You just found the area of a rectangle. But the area of that rectangle, and if you take this thing and flip it over in here, the area of this triangle, they're exactly the same thing. So finding the area under the triangle is exactly the same thing as finding the average force times time. And that finds the change in momentum for us. So here's the thing you're supposed to be able to look at. If distance equals average speed times time, which it does, and if the area underneath is touching that. Okay, thanks. So you're supposed to recognize the similarities here. Distance equals average speed times time. Change in momentum equals average force times time. This force goes on this axis, time goes down here. Speed goes on this axis, time goes down there. See how those work the same? Instead of taking the average number times the time, you can just take the area underneath the graph instead. Hey, that looks kind of familiar. How something equals a something average times a distance. How something equals a something average times a time. Speed goes there, time goes there. Force goes there, time goes there. Can you take our equation when we have it says work equals average force times distance? What particular graph might actually do something for us? A graph of blank versus blank. Yeah, can you see the similarity? Force goes over here, time goes down there. Average speed goes over there, time goes down there, and it's going to have to. So if you draw a graph of force versus distance, and sometimes the force is the same all the way. For the most part, if I lift this up, it doesn't get heavier as I lift it up. The force is the same. So if I drew a graph like that, it would be a horizontal line, no big deal. But what about something like this? Did you know that as you pull this back, it gets harder and harder and harder? So the force gets bigger. So a graph of something like that would look more like that. And if I want to figure out how much work I did, I could either take the average force times the distance, or, as we have just seen, in other examples, I could also take the area underneath that thing. So the area under a force versus distance graph is the same thing as taking the average force times the time. So there's 3 examples in a row of how that works exactly the same way. And there's a lot more of those in physics. We may get a chance to see them right now. There's tons of times when that shows up. All right. One more section here, we'll take a little bit of a break. We skipped power, but we're going to spend a ton of time on energy. This whole chapter is going to work and energy together. Turns out, here's the short story made easy. I just did some work. I just stored some. When you do work, you store energy. When I do work, I just gave this thing energy. I do work, I stored energy. What can we do with it? Do some fun stuff. And there's energy stored waiting to come out. So when you do work on something, you give it energy. Probably a better word than give would be transfer. I give energy to the object. So I gave my energy to this thing, and then if we're going to use this, we probably put a little ball or something with. I'm going to shoot something. There we go. Okay, that's a little big, isn't it? I'm going to go through there. Look at that all the way though. I'm not going to work. Alright, it's going to work. Barely. Alright. So the idea was I gave energy to this gives energy to the ball same in the earth need energy, we just keep transferring energy all the way through. So when you do work on something, you give it energy, it now has more energy than when it started. Mr. Chujo confiscated this from the cafeteria one day. It didn't have the duct tape on it. It is cool. He said, "Hey, cool. Let's not waste any more spoons." When the students had done, they had rubber bands. I just took the duct tape and put it on there. It is a pretty cool idea. Did I just do any work? I don't know. Let's see. Did I exert a force? Did I exert a force and move something over a distance? I did. Now this thing has energy that it didn't have before. Okay? So when you do work on something, you give it energy, you store energy in it, and it turns out that energy is nothing more than the ability to do. Any guesses? Work. I'm not saying you're going to, but when you have lots of energy, you can do lots of work. Some people don't choose to use it that way, and I get it, that's fine. God, it's so energetic day, I'm going to go play instead. But you could do lots of work. And when we do work on an object, we change its energy. Yep, when you do work on something, you give it energy. Let's see. Let's see how this guy goes. Oh, am I doing any work? Yeah, I'm exerting a force. And you'd have to trace a small circle, wouldn't you? Do you know how to find the distance around the outside of a circle? It's called circumference, yeah. But the idea is I'm exerting a force, and you could trace that distance. It's actually more than one circle, a bunch of circles. And then I can see, does he have any energy? Yes, he has energy now that he didn't have before. Okay. Not doing a whole lot of work with it, but I suppose he could. You give him a broom, he could sweep, I suppose. Let's do it. Yeah, he could stir the pot or something. Alright. I hate to give it away on day one within the first 25 minutes, but here's the most important idea in this whole chapter. If I do 2 joules of work on this thing, it now has 2 joules more energy than it used to. Be careful, it doesn't have 2 joules, it has 2 joules more than it used to, because I don't know what it had before. So if now it has 5, and I do 2 joules of work, now it has 7. Basically what we just said is, look, when you do work, the amount of work that you do on something, and the change in energy of the object, okay, the amount of work you do on something, and the amount of change of energy that an object has, guess what's true about those two? They're equal. Yes, they are equal to each other. We've kind of flown right by it, but that's why we measure energy in joules and work in joules. They're actually measured in exactly the same units. Because it takes one to do the other. It takes energy to do work.
So how many diamonds?
I don't know. If we could trace that through, let's go this way. I just did 2 joules of work on this thing. It now has 2 joules more than it used to, but I have 2 joules less than I used to. Boy, am I tired. Just kidding. But where did I get that energy? From the food that I ate. Right? Where did the food get the energy? From the sun, from photosynthesis, and probably from the nutrients in the soil. Okay. All right, I'm gonna do some work. Can you see that I'm giving you some energy? Because it doesn't light up when you don't do that. And the distance wasn't a lot, but it did lots of time, didn't it? And this one gets a little harder as you go too. So if I took that distance, the distance I actually care about is that distance times whatever it did, 20 times, and you can figure out the work that they did. And now, ooh, this thing had energy, but now it spent it on the ceiling. And now the ceiling is just a touch warmer than it was before, isn't it? Well, not a lot, right? You can't heat up the whole room by doing this, but the energy had to go somewhere. So whenever you do work on something, you change the energy object, and the amounts are exactly the same. That's why they're both measured in joules. The amounts are exactly the same. All right, why don't you stand up and stretch for a minute? More demonstrations.
You know what I always found funny, Mr. Jones?
Yeah.
Well,
Okay. Oh, okay.
So I need a definition of energy as capacity to work.
Okay.
Because someone
Is it?
may take in front of the fact that sci-fi is
Oh my goodness, did you guys?
that's like saying something related to show.
It must be fire. Do you want to know what
Well,
happened?
careful.
I was playing yesterday. I have like this really smart assassin build. I changed my melee build to assassin. Smart.
They get
And so what happens is I can
yeah, but we get more of like
I can hack robots now and make them self-destruct. So I made a video in my week and I went and hacked a robot and made it self-destruct. And then in the corner it says Aloha snack bar.
spring break.
I think there's a day in March.
It was pretty
Well,
fun.
and Rachel, are you gonna be gone Thursday?
Yeah, I love it.
Yeah, it's find time to make up a lab.
Okay.
Maybe
I'll
even
see.
ties tomorrow, and you'll have all the information by the next possible.
Aren't we taking some
Oh, you're
like
right. Dang it, thanks for reminding me. Yeah, you're right.
something with the computer should take a survey.
That builder will be able to like do everything with robots, hacking,
You know, where it's like
computers, and lockpicking. And
yeah. It's like the one. I don't know. It might not be that. I don't know what it is.
It's a survey that you have to take when you're a freshman in juniors. So it's kind of what assessing to be too last year.
That one with really basic questions. Yeah,
Well, yeah, another building's right now.
fun again.
Yeah, that was taken.
Are they seriously?
Yeah, did you not hear all the sirens? Yes.
Yeah.
Alex is probably celebrating right now.
Okay, Howard was like, yeah, I gave you a competition. It was probably someone from there.
There's something.
Alright, here's some more examples here.
Free market system works.
And they're wrong. They didn't use it.
Alright, some more wind-up toys. I do work, I give it energy, and I lose. But lose is probably not a great word. I transfer energy, like transferring the bank account, right? And what can he do now? He can roll across the desk. That's outstanding.
It's a nice water.
What does this thing do? Again, the same kind of thing. I'm doing work, giving it energy so that it can go now do some work. Right? Let me crash through a wall or something. Right? Wind up toys are very good. Let's see. Did some work. I just stored some energy. And now maybe we could release that energy in a different form. If I don't do that, it doesn't go very high. Right? Store lots of energy. In fact, instead of stored energy, we're going to call it potential energy, right? And potential is sort of would, could, ready to, but hasn't yet. Right? And then you can, sometimes it does it right away, sometimes it waits. But when I did work, I stored energy, and the amounts are about right exactly the same. Sometimes that energy takes a little bit to come out. Sometimes that energy comes out right away. But either way, it's transfer energy from me to the object itself. While we're here, we're going to talk about 5 kinds of energy. And we're going to spend most of our time on one. In fact, you already spent 2 trimesters talking about chemical energy. You've already done that. Chemical energy is stored in the bonds between the atoms, between the molecules, stuff like that. And when you watch a firecracker explode, that's chemical energy being released. When you watch something burn, you ever seen anything burn before? Just kidding. I prefer not to burn myself.
There you go, guys, that's chemical energy.
Is there any stored energy in here? It's an almond. Yeah, I think it's an almond. There's stored energy in there between the bonds and the atoms and the molecules.
Roasted almond.
Kinda, yeah. And we can take that energy and, well,
So dank.
release it, so to speak. So that chemical energy is being transformed into other kinds, like heat. Light's a form of energy as well, turns out. Yeah, a little bit of sound. Probably can't hear it back there, but I can hear it crackling a little bit. Yeah. So we're just transforming energy from one kind to another. This time I didn't have to do any work at all. I didn't have to do any work. The energy was already, so to speak, stored in there. Or it's releasing. Does this go back to your calorimetry unit in chemistry? Convert, yeah. Oh, yeah, flame is coming in then.
So,
For now.
Sharp the first name, so that the white player.
No, I had it ready for that anyway. So his whole idea is go back to chemistry. Was that exothermic or endothermic? So energy was exiting, coming out, is one way to look at it. Okay? Yeah, nice. All right. So that's one kind of energy. Heat, thermal is another kind of energy, right? There's only, because it turns out there's only 5 types for us. So we just transformed chemical energy into heat or thermal energy. The difference between a transfer is I give the object energy, right? I just transferred energy, versus a transformation is from one form to another. So I didn't have to do any work in this case. All I did was transform the energy from chemical to light and heat, things like that. So that's the difference between a transformation and a transfer. Weirdly enough, a transformation is from one form to another. That's why they call it that. Electromagnetic is the weird kind. It's hard to see it. Well, most of the time it's hard to see it. So it's energy transformed as invisible waves. Basically, you're going to recognize electromagnetic energy as electricity, light. And any kind of light that we can see or not see, even microwaves, radar, all that stuff, those are all electromagnetic waves. So really, we should say that the energy here was transformed from chemical to electromagnetic and heat or thermal, plus a little bit of sound. Flip it over for a minute. There's 2 more types of energy on the back.
What's that thing?
Yes, it is. All right, nuclear energy. That's kind of obviously in the nucleus of an atom, and you're not going to see any of that here. Sorry. You're not going to see any transformations to or from nuclear energy, but we know that they're there.
maybe just look up on nuclear.
Well, because the question is this: what's in a nucleus?
Energy.
Okay, what things are in a nucleus? Sorry, bad question. What things are in a nucleus?
Protons.
Protons and
Neutrons.
neutrons. So here's 2 protons. What do they do to each other? They repel each other. Here's 2 neutrons. What do they do to each other?
Nothing.
Nothing at all. Here's a proton and a neutron. What do they do to each other? Nothing. It's well, positively charged and neutral. They don't do anything to each other at all. Let's put them in a nucleus, okay? If you look at every 2 pair of objects, these are neutrons. What are they doing again to each other? Nothing. What are these 2 doing to each other?
Oh,
All right. A proton and a neutron. What do they do to each other?
Nothing.
Nothing. But what do the 2 protons do to each other? Oh, they repel each other. So what's the only kind of forces going on that you know of so far? Is repelling, and yet these things stay in a nucleus? What keeps them together? Yeah, the electrons are way out of the periphery somewhere. Electrons do not keep this together. There's something else called the nuclear force that you haven't learned about before. That's what keeps us together. But if you get really big nuclei, there's too much repelling, and eventually it just falls apart. And that's when you can see the effect that the nuclear energy is changing to something else. They change, we're going to say transform. We're going to spend most of our time, in this class, on mechanical energy, because this is a class about moving things. So mechanical energy is either moving or could be moving. So moving or could be moving. Either moving or could be moving. Pull the slingshot back, and then we've used wind-up cars, haven't we? Did I just do some work? Yeah, I moved this thing, exerted force. Think there's any energy in there right now?
Yep.
Yeah, we're going to use the term potential energy. Could we change it in another form? Yeah, it can go on. So we're going to spend most of our time in here on mechanical energy. Bows and arrows, wind-up toys, stuff like that. We've already covered a lot of the other kind before. You don't have to write this down, it's already there, right? It's the same stuff that's up on the board. Energy can either be transformed, which means change from one form to another, or it can be transferred, which means from one object to another. I put the bowling ball away, but you've seen the bowling ball many times crash into something. When a bowling ball knocks something over, it transfers momentum and it transfers energy, right? At the same time, just both exactly at the same time. So let's take a look at some more energy transformations. How about this simplest thing I can find up here? Alright, here's a light bulb. And amazingly enough, when we plug it in, the light bulb comes on. Gosh, this apparatus starts with what kind of energy? Electricity, which is really electromagnetic, and transforms it into heat, I mean, it gets hot, and light, which is also really electromagnetic. So it's a transformation, transforming from electricity into light and heat and a little bit of sound. I won't put it too close. Okay. Let's try this. So that thing inside that bulb right now, once it settles down, there's no friction in there hardly any, so it doesn't work. It's not moving. If I put this close to it, ooh, it actually stops, and now it's going to turn around and go the other way. Why? Because one of those, every pane, one side is painted black, and the other side is painted white. So some of the panes are absorbing all of the light energy, and some of the panes are reflecting all of it. So the analogy, it's not a great analogy, but it's not bad. If I sat on a stool, and I gave you guys a bunch of the tennis balls to throw at me, and one hand always just caught them, just hung on to it, wouldn't that be like the black pane that just takes the light energy and absorbs it? And the other hand, every time it caught a ball, it threw it back. Isn't that like the white panes that take the energy and re-emit it? What would happen if I sat on a stool and did that? Really? No, I bet you I'd spin around. If you catch one on one hand and the other one always throws them back, you start to spin eventually. That's what that thing does. I wanted to use this. It seems like there's a short, and I can't seem to get it to come on. Let's see what happens. Oh, there it is. Yeah, there we go. Alright, here's a short somewhere. Does this work? Oh, that works way better, doesn't it? Oh, now it's spinning like crazy. In fact, as long as it's working, let's take this guy. Oh, I wish he rode the bicycle, but his head just spins instead. Sorry. Alright, so let's just check. Is both of these objects take in what kind of energy? Okay, yeah, electromagnetic. It's light. Let's say light for now. It's electromagnetic, you're right. And transform it into?
Mechanical.
Mechanical is moving or could be moving. So both of those objects transform energy from light, which is really electromagnetic, into mechanical at the spinning round. Okay? This thing actually has a name. What's it called? A radiometer. I've had people on the test talk about the black and white spinny thing. Okay, fine. If all you remember the black and white spinny thing, that's fine. This is the bicycle guy we talked about. Again, I wish you could really ride it, but I think it's too heavy to do that. I think is the idea. Which is why I just don't have it work that way. All right. Let's see what we have here. We have two 1 pound, 2-inch diameter chrome steel-plated spheres. And when they're smashed together, enough heat is generated at the point of contact to burn a hole in a piece of ordinary paper. Got any ordinary paper? Hey, there's some ordinary paper. Cool, let's take these out. 1 pound, 2-inch diameter, chrome-plated steel spheres. Hang on to that. I probably won't hit your hands, I'm pretty sure. Normally I come around and try to stay in the video here and see. Yeah, smell that. See what you think. Smell it. Smell. You ever had a cap gun when you were a little kid?
Oh,
You shoot the cap. I can almost smell it from here. Yeah. Let's try a couple. I wish we'd catch on fire. Just not gonna happen. But if you look at the edges are a little brown. Right? It's not like on fire like the pecan was, but it's definitely. Just keep doing it. Eventually, if you're stuck out in the woods, you're gonna start a fire like this. I doubt it. It does sound. Well, let's go through the energy stuff, so to speak. Where did these things get their energy? From me. Where did I get it? From the food. So let's take food is what kind of energy? Chemical energy. And I transform it into mechanical energy. These things take mechanical energy and transform it into heat energy. Okay, those are all. So transformations and transfers. So I transformed chemical energy in my body in mechanical energy. These things take mechanical energy, transform into heat energy. In addition, I transferred energy from me to these, and they transferred energy from them to the paper. So there's both going on, transfers and transformations both at the same time. That is amazing, huh? Oh, here's another toy. Let's see. Looks like this guy, you just push his head down, I think. Let's see what happens. I just did some work, boy, am I tired. There he goes. Right. There's all kinds of wind up toys up here for stuff like that. Oh, gosh. Alright, how about a fire piston? Whenever you hear the word fire, everybody gets excited. Right? I wish it would be a big explosion. It's not going to be a big explosion. But here's the idea. It's a piston. And we can open it up. What a cool sound. Take a small piece of cotton. It doesn't take much. In fact, I've had this piece for probably 10 years now. And you just rip really small pieces of it out. Okay? Piece of cotton. I'm going to put it in there. Alright. Two things are in there now. Cotton and air. Yeah, air's in there, better be in there. Right? And the idea is, once I close this off, I'm going to push down on this. I'm going to do some work. And when I do work, I transfer energy. Well, I'm going to take mechanical work I'm going to put in. But inside there, that work's going to get transformed into, any guesses of the 5 types?
Chemical.
Could be chemical. It's not going to be nuclear, right?
More mechanical.
We want nuclear power.
What do you think might happen to the air in there if I do work on it? It might
So compressed.
heat up. That's the idea. It get compressed, but it might heat up. And if it gets to a high enough temperature, maybe that cotton in there could catch on fire. It's not a huge explosion. I wish it were. I'm going to turn the lights off just so we can hopefully see it over it.
And there's diesel. Way more compression.
Yeah, go ahead and scan out. That's fine. If it doesn't work the first time, don't boom me. Let's try it again, alright? And let's see what we get. That's it. Sorry, that little, that's all you're gonna get, right?
A big piece of cotton.
Yes, yeah.
I don't, well, in fact, I know I can't. Once you do that, you guys should know this. Aren't there waste products in there? Any more oxygen? They already probably used a good portion. I can try it again. I cannot believe it'll do anything. Ooh,
No.
actually, I couldn't even push it all the way down again. That's fun. It does look to me like we didn't use up all the cotton, though. Oh yeah, there's still a decent sized chunk in there. We get away with the waste product, maybe? It might work again. I can still see some cotton left in there, so we definitely did use it all up. Can you see that still there? Let's see what we get. Oh, that's a
That was a
good
big
one.
one.
That was a better one. Okay. And you can see smoke, probably ash over in there as well. Let's go back up.
And there's a diesel engine runs away.
So once again, when you do work on something, you transfer energy to it, and that energy can be in lots and lots of different forms.
Unless you stop it.
I'm glad I bought that. It's kind of stupid that we bought this, however. This is a sack of copper shot, like a BB. You know what a BB looks like?
Oh, yeah.
So there's tons and tons of little pieces of copper in there. They're not even all the same size or shape, and it doesn't matter. You know, there's one right there, a piece. I know. I didn't know what I was getting for sure. Here's the directions, seriously. You take a thermometer. I just have a thermometer up here.
Yeah.
There, that's good. And you take the temperature of the shot. I gotta go doctor. Okay, great. What you're supposed to do now, seriously, is drop it 100 times. You're supposed to do that. Yeah, and I'm gonna drop it. I've already got, can you listen to this? The whole bottom of the box has it all over the place, so I'm not gonna drop it again. I've already had holes in the bag like crazy. Drop it 100 times. 99, 100. Stick the thermometer in the right way. Guess what you find out? The temperature went up like a half a degree. It's not a lot. You can't warm up copper shot a lot by doing that, but the point is you can transform energy from mechanical into thermal. Yeah. So that's that energy transformation. In addition, I'm transferring the energy from me to it. Right? So that's energy transfer. In addition to energy transformation.
So if you kept doing that long enough,
Then maybe the copper would melt. Now, if you kept doing it long enough, unfortunately, some of that heat energy leaks out into the air, doesn't it? And yeah, so if you did it in vacuum, it would probably work better.
you did it fast
If
enough.
you did it fast enough? So you're just saying, I'm not fast enough doing it, you might be right.
You know, just like get a giant camera and snap.
Alright.
Yeah, but you melt eventually.
I don't know if you guys saw this in chemistry or not. It depends on who you have in chemistry. I need a little bit of alcohol. I don't mean for me, I mean for this. And luckily, we have a whole container. Not a lot left in it, but there's some.
The website just has like 2 John. Oh.
Not that much, I don't think. No, alcohol evaporates so quickly.
Well, that's okay. That's not right.
No, it's
You just left it open.
Alright. Alcohol is a chemical. It's got stored, we're going to say, potential chemical energy. But it's not the liquid that has a problem, right? Liquid gas doesn't burn. It's got to be in vapor form. So I'm just going to hang on to this for about 30 seconds, and hopefully the heat from my hands will make the alcohol in there evaporate. Stay inside here, though. It'll stay inside the container, but I need it in vapor form. And then, you know what the starter looks like on a grill you have in your backyard? Push it. When you do that, a little spark comes out the end. So we need something to get this reaction to go, but that should just do it. We'll see. Sometimes this works, sometimes it doesn't. Let's see if we can transform chemical energy into other forms. Nope, didn't go. Alright. Hang on to it for a little longer. I don't know if we need more. I didn't think we needed any more alcohol than we already had. I suppose I could check. You want to check and see where that spark's going? You want to check and see whether it's actually sparking? Sometimes that's not a good idea. It hurts. Nope, still didn't go. Alright, let's try this and see why it's the case. Maybe we'll try a little more alcohol. Let's see. Nothing sparks anything. That could be. No, there's a little spark going. Alright, we'll try just a touch more. More is always better, right? Oh my gosh. Alright, that's enough for 12 of these. Most of that. Here, I'll pour it on the desk. Should have poured it back in, but you really can't. Alright. This is alcohol. What's it going to do pretty quickly?
I like burning things.
Even that's too much.
Yeah.
Unfortunately, there's alcohol all over everything. You know, one time I actually got this to work with the hand sanitizers that we use. Because isn't it something like 60 or 80% alcohol?
Yeah, I think it's like 100.
What does it say? Well, I can't remember. We got 70% alcohol. Yeah. So we've had that work before. I just need it in vapor form. The liquid form doesn't help.
Try shaking it.
Minty flavor.
Alright.
A little, ew.
Yeah, kinda. Alright. See if we get anything at all. No? Darn it. Alright. I'll come back and try it again later. It's a pretty cool explosion when it works. I'm just not sure why it didn't. Let's see. Because I'm going to shut that off because I feel like it's dragging anyway.